Hello children, welcome once again. In the previous video we have learned about Euclid division lemma or Euclid division algorithm. And that is the first most important concept of our mathematics, 10th class mathematics, and in this session we are going to learn about second concept, fundamental theorem of arithmetic. This is also most striking features of our mathematics, in fact our first chapter. So learn it carefully and try to understand by careful observation, right? Okay. Fundamental theorem of arithmetic. Its statement goes as follows. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So every composite number can be factorized or expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So at this moment you may have little difficulty to understand this, but in the due course of time you would understand it better. But before that you must be familiar with things like prime numbers, composite numbers, odd numbers, even numbers, etc., etc. But anyway, don't worry, we're going to have a clear explanation. So this is otherwise known as prime factorization. Fundamental theorem of arithmetic speaks about prime factorization. You did this unknowingly or knowingly in your earlier classes. Let us try to understand fundamental theorem of arithmetic or prime factorization by means of these examples. So suppose let me take 140. I want to split 140 as the product of primes. See here, 270s, okay, 235s. I had to take prime numbers only. Here I cannot take other composite numbers, 5 sevens. Now what happened? 140 is equal to 2 into 5 into 7. Look here, 2 2s are 4, 4 5s are 20, 27, 40. So 140 has been factorized into prime numbers, prime factorization. Right, this is what prime factorization means. You did it knowingly or unknowingly. But here, oh, okay, why should I start with 2? I know big tables. So 720s, okay, you can start like this. 720s, I will take 4, 5 4s, 2 2s. So 140, this time I will write as 7 into 5 into 2 into 2. See, observe carefully. So here we have 2 2s, here also we have 2 2s. Here 1 5, here also 1 5, here 1 7. The same numbers appear here also. But order is changed. Okay, sometimes you may like to do like this. I want 10 14s, sir. Okay. Again, you have to make, because this composite number, you have to make it 2 5s. Prime numbers only should appear. And this is 2 7s. Now see, 2 5s, 2 7s. Same numbers, 2 2 5 5 7. Same numbers will appear in whatever way you do. That's what fundamental theorem of arithmetic is telling us. Every composite number, if you take prime number, you have nothing to do with it. Suppose if you take 17, nothing to split. 17 you can't split it. So itself a prime number, nothing to deal with. But if you take composite number, you can make it or you can express it as a product of primes. That's what it is telling. You can express it as a product of primes, and this factorization is unique. Apart from the order, okay, numbers may change this side and that side, but the same numbers will appear in whatever way you do. That's what fundamental theorem of arithmetic is telling us. Okay, you can do with other numbers. 156 you can take. Let me do 5005. 5005, how can we split 5005? Let us try. You can start with 5 1001s, right? 5 1001s. And which table will do 1001? This is a bit tough one. I hope 7 will do, right? 7. Let me take 7 1s are 7. 7 14s are 98. Yes, 7 143s. And what about 143? 11 table. 11 13s, right? So 5005 is 5 into 7 into 11 into 13. Understood? So this is what prime factorization. You may start differently. You can start with some other table or 7 or 11. You can start with 11 also. But anyway, you arrive at 5, 7, 11, 3, 13. These are the prime factors that exist in 5005. This is called prime factorization, or expressing as product of primes. So what's the statement? What is the statement? Fundamental theorem of statement. Every composite number can be expressed or factorized as product of primes, and this factorization is unique apart from the order in which the prime factors occur. Right? Okay. And what do we do with prime factorization? I asked the same question when we learned about Euclid division lemma. What do we do with Euclid division lemma? We find HCF in the same manner. Here also we're going to find HCF and LCM of two given numbers or any given numbers. How can we find HCF and LCM? Here is a procedure with this prime factorization. HCF is equal to product of the smallest power of each common prime factors of the numbers. Don't worry, by means of example you can get clarity of this. Product of the smallest power of each common prime factor of the numbers. That means we are going to prime factorize each number, and then we extract HCF from those. And in the same manner we find LCM like this, product of the greatest power. So observe the difference, smallest power HCF, greatest power of each prime factor. Observe the change. In the HCF we use each common prime factor. Here we used each prime factor of the numbers. I will explain you all these things by means of example, right? Right, with the help of prime factorization or fundamental theorem of arithmetic, we are going to find LCM and HCF. Example, find LCM and HCF of 72 and 108 using prime factorization method, right? 72, how can we split it? To 36, to 18s, to 9s and 3 3s. So 72 is equal to 2 into 2 into 2 into 3 into 3. This is otherwise written as 2 cube into 3 square. Got it? 2 comes 3 times and 3 comes 2 times. 2 cube into 3 square. And what about 108? 108 ambulance. Ting, 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 ting. 254s, 2 27s, 3 9s and 3 3s. So what about 108? 108 equal to 2 into 2 into 3 into 3 into 3. That means 2 came 2 times and 3 came 3 times. So using these as we have prime factorized them, using these we try to find HCF and LCM. So what is HCF? HCF is equal to, our definition, product of the smallest powers of each common prime factors. First we have to pick common factors from both lines. What are there? Yes, both are there, 2 and 3. But among them we have one is 2 cube and one is 2 square. Definitely 2 square is smaller. That's what we had to pick. 2 square. This is the smaller one, 2 square, because we have definition, product of the smallest powers. And among between 3 square and 3 cube, what is the smallest? 3 square. So 2 square into 3 square. That means 4 9s, 36 is the HCF. You can verify it. And what about LCM? We had to pick each greatest power of each prime factor. That means we have one prime factor 2, and among that 2 cube is the biggest one, and we have 2 and 3 prime factors. Here from 2 and 3 we have to pick the big ones, 2 cube and 3 cube. That is LCM. That means 8 27s, right? 3 cube means 27. 3 3s are 9, 9 3s are 27. Not 3 3s are 9. Or 2 cube means not 6. 2 3s are 6. Many of you doing 6. No, 8. So 827 56 216. This is HCF, I mean LCM. This is the way to find LCM and HCF. Okay, I'm going to explain you with one more example. Now 306 and 657. Find LCM and GCD. Let's try to find it out. First 306 is 306. Let us split this to 153s. Okay. To 351s, and this is 317s. That's it. Okay, so 306 became 2 into 3 square into 17, isn't it? I think you know how to write this. There are 2 3s, only 1 2. Okay, 17 also only 1 there. And what about 657? Okay, I am using 3 table. 3 2s, 2 19s. Again 3 table. 73s. 73. It's a prime number. Nothing will go in that. 73 can't be split. 657 is equal to 657. Right again. 657 is equal to 3 square into 73. Right. What is GCD? GCD or HCF? Both are same. Okay. Don't confuse that. Greatest common divisor, it's highest common factor. Both are same. HCF, how will we find HCF? HCF is equal to, we have to pick common factors from these two. What is common? Only 3 is common. Okay. And out of those smaller one, both have 3 square. So 3 square. That means HCF is 9. 9 is the HCF of 306 and 657. But what is LCM? Okay, this is a bit tough. We have to pick each prime factor, but among them biggest. 2 anywhere? No, only one place, that is 2 power 1. 3 anywhere? Okay, 3 square, 3 square there, but anyway 3 square is bigger. What about other? 17? Okay, 17. Only 117. 73? Only 73. So you have to 2 into 9 into 17 into 73. You have to find all these things. Multiply it yourself. You will get LCM. So this is the way how to find LCM and HCF of two numbers. Understand? So from HCF, for HCF, we pick common factors, common prime factors, but out of the smaller ones. If there is no common ones, for example, if anyone asks you to find HCF of 16 and 17, what will you write? 16 is equal to 2 into 2 into 2 into 2. 4 2 is there. 17, nothing is there. What is common? Nothing common. Here no common is there. That's why if nothing is common, their GCD is 1, their HCF is 1. You know that. They are called co-primes or relatively prime numbers. Okay, that's different topic. But how to find HCF and how to find LCM by means of prime factorization is very important. Learn it. Don't forget. Okay. Right. And one more, so that I can conclude this. Find LCM and GCD of or HCF of 12, 15, 21. This looks a little bit easy, right? 12. 12 means okay. 2 6, 2 3s. That means 2 into and 2 square into 3 power 1. What about 15? Oh, we have a straight arrow, 3 5s. What about 21? Again, we have a straight arrow, 3 7s. Now, what is the HCF? You have to tell. What is HCF? You need to find common factors. 2, not common to all. 3, yes, there is 3. 3. Out of those small, anyway, 3 power 1 is only 3. 3 power 1 or 3, same. HCF is 3. That's it. No other number is common to all the 3 except 3. Okay. What about LCM? Now let's try to pick LCM. LCM means we have to write product of greatest power of each prime factor. Each prime factor we have to take, but if you find any 2, you have to take bigger one. Suppose here 2 square, no 2 is there, therefore we take 2 square. 3, We have same 3 and all, that's why 3 power 1. If suppose 3 square is there in different one, we take 3 square. If 3 cube is there, we take 3 cube, big one we take, but only ones we take. 5, nowhere, but we have to write 5. Here not common factors, you have to write all factors, but among those, if 2 factors are same factors are there, in that you have to pick big one. That's the difference. I think by this time you got it. Now 2 square means 4, 3 power 1 is 3, 5, 7, 4 3s are 12, 12 5s are 60, 67s are 420. This is LCM. This multiplied, previous one left because it's big one for you. This is what we are going to do in prime factorization method. We find LCM and GCD of numbers, right? And one more example, last example. Let me finish. Check whether 6 to the power of n can end with the digit 0 for any natural number n. What is 6 power n? That means 6 power n means in the place of n you put any number, natural number. 6 power 1, that means 6. In place of 2 n, if you write 6 square, that means 6 6 are 36. In place of n, if you write 3, 36 6 3 times 216. Likewise, if you change the place of n, with different natural numbers, you will get to 6 36 216 another number. So whenever you are writing like this, will you ever get last digit 0? That means here 6 came, here 6 came, here 6 came. Will you get last digit 0? Obviously no sir, every time we'll get 6. But you have to confirm it. By using this we'll confirm. How? 6 power n is equal to, we'll write 2 into 3 whole power n. If any number is to end with 0, that means like 20 or 300 or 420 or 600, 6050. If any number wants to end with 0, it should be an even number, isn't it? Or must be divided by 2. Definitely must be divided by 2, and at the same time must be divided by 5 also, right? So 2 and 5 must be the factors of the numbers that have 0 as its last digit in units place. In units place, if it contains 0, when you split it, you will get 2 and 5. Try it out once. So that's why here, since you have 2 but do not have 5, so 6 power n never ends with 0. You never get 0. So if any number's unit place is to be filled with 0, that number must have 2 as well as 5 as its prime factors, or else it never ends with 0. That's what this particular question means. Okay, right? I think you understood. Try it with the textbook questions and you will learn it better. So Euclid division lemma and fundamental theorem of arithmetic, both are very essential. Understand and learn and use for various applications. Thank you for watching this video. Bye bye. Vinay, mathematics teacher.